If we distribute, however, on the bottom component, we see that this comes out to be alpha k and alpha k plus alpha times 1, or alpha k plus alpha. So there's a little bit of strategy involved here because we need to now make an argument. Does this live inside of V? Question mark. So in order for it to live inside of V, these two elements right here, the bottom and top component, must be separated by a difference of 1. However, if alpha is not equal to 1, then alpha x does not live inside of V. So only when alpha is 1 will this be true. If alpha is, let's say, 3, then we'll have 3k up here, and then we'll have 3k plus 3. And those are actually 3 units apart. So for varying alphas, we'll have elements that are varying a number of elements apart. So in general, if you take a vector inside of here, and you multiply that vector by alpha, then you end up with a vector that is not necessarily inside of the set. You end up with some other inside of some other range that's not the same as the domain. We could do a similar proof for x plus y. So how do we do this? Well, let's say that x is the vector, and we'll write it this way. We'll say it's k1 and k1 plus 1 down here. So again, that's just, we need to make sure that x resides inside of V, and the horizontal and vertical components need to be 1 unit apart. And if we take y is equal to k2 and k2 plus 1, then adding these together will yield a vector of the form k1 plus k2 on top, and k1 plus k2 plus 2 on the bottom. And we can see right away that we have the same component on the top and bottom, but these vectors are actually has a vector in which the components are 2 units apart. So how does this work geometrically? Well, if I pick, for example, the vector 1, 2, so essentially any vector where these are 1 unit apart, so I could also pick, let's say, another vector, let's say 2 and 3. Okay, so 2 and 3 will produce a vector up here, and those vectors are not necessarily, or are not collinear. So if I add them together, their sum, and that wasn't a very good illustration, let me try another one here. We have 1, 2, 3, 1, 2, 3, 4, and we have the vector 1 and 2, and then we have the vector 2 and 3. We can see that these two vectors are not collinear. Now, when you add them together, you get a vector that represents the sum of the components, which formulates this vector right here, which points somewhat like this. So no longer is it the case that that vector will necessarily have horizontal and vertical components that are 1 unit apart. And we see that here. In fact, any two general vectors will then be 2 units apart for their horizontal and vertical component. So our definition is kind of a little too loose. We have kind of made this a little bit more concrete. We've said that we need to verify 2 properties for whatever the set is, that if I take a vector inside of the set, I multiply it by any real number alpha, that must be an element inside of V. Got to make an argument. If I take 2 vectors, x and y, that are both elements of V, and I add them together, the result must be in V. If they're not, the world doesn't explode. However, this set cannot be considered a vector space. Now the theory, which is kind of beyond the scope of what we're going to examine here, but the theory requires some axioms to hold. There are some additional things that we actually need to verify. Now hold on tight, because there's quite a few of them. So in general, in mathematics, a vector space is a set V on which the operation of addition and scalar multiplication are defined, with each pair of elements x and y and inside of V, and real scalars alpha and beta. We have unique vectors x plus y, or alpha x, that also reside in V. So that right there is just our 2 properties that we've been verifying. Those are the 2 most important properties. This set, together with the 2 operations, form a vector space if the following are satisfied. That these are all properties that we are familiar with. This is the associative property. This is the, I take that back. This is the commutative property, and this is the associative property. And then this is the what we call typically one of the identity properties, that if you add the equivalent to 0 in that set to x, you basically still get x. So a lot of these properties are ones that you can oftentimes do hold. In fact, we already know that for vectors and matrices, these properties hold since matrices and vectors inherently have these properties. We already know that these properties hold, that if I, for example, scale the sum of x plus y, I could scale x, scale y, and add the results together. These are just properties that vectors and matrices have. The deception here is that you don't necessarily need to be working with vectors per se in order to call a set a vector space. A vector space can be a set that doesn't have any vectors at all. So we're not going to spend the time verifying these because assuming we're working with vectors and matrices, they all automatically hold. However, vector spaces can be applied to functions and other algebraic structures, so they do not always hold. There are situations where, oddly enough, the abstraction of a plus sign, plus doesn't necessarily mean to add in the strict sense, and scalar multiplication doesn't necessarily mean multiply in the strict sense. We're not going to go into that here, so we're not going to verify these. But in general, for a vector space, you need to make sure these properties hold. We're just lucky because with vectors, this works out. So maybe let's take a look at one more here where we are dealing with vectors. Now those 7 axioms, these 8 axioms, we know hold because we're dealing with vectors. If we add together 2 vectors, it doesn't matter what order we add them in, et cetera, et cetera, et cetera. So here we have a 3-dimensional vector, the vector w, 2w, 3w, such that w is a real number. So we need to check 2 properties. Number 1, does alpha x live inside of V for any real number alpha? So I'll put a question mark. All right, well, let's take x to be the vector. We'll call it k, k1, 2k1, and 3k1. So basically any vector that's a multiple of the vector 1, 2, 3 will work. So alpha, if we scale this, we get alpha x equals alpha k1, 2 alpha k1, and 3 alpha k1. Now, one thing we again know is that if we multiply 2 real numbers, you still get a real number. So if we say w is equal to alpha k, and clearly w is going to be a real number because we're taking a real times a real, then this is in fact another vector that's inside of the set. So alpha x is also, if I scale that vector, I get another vector that's still inside of that set. So that checks out. Property 2, if I let x be the vector, we'll say k1, 2, k1, 3k1, and I let y be the vector k2, 2k2, 3k2, just to differentiate them, and I add them together, what I get is k1 plus k2, 2k1 plus 2k2, and 3k1 plus 3k2. Now again, a lot of times you have to do a little bit of algebra on it to make it look like a vector of this form. And right away we see that again we could factor out from each of lines 2 and 3 a 2 and a 3 respectively. And we see that these 3 pieces are all the same, and therefore if w is the sum of k1 and k2, then this vector x plus y does indeed reside inside of V. And so that checks out, so this is a big yes. Okay, we would need to check those 8 axioms, but since all those properties hold for vectors, we're in good shape. What about where we're not actually dealing with vectors? What about linear functions? Well, first of all, we've got to think about what we think of as a linear function. In general, we would call this something of the form mx plus b, such that m and b, also I'll write it this way, m comma b are real numbers. So any real numbers will do. 0 function is still a linear function. A constant function is a linear function. So now this is not as tricky as it seems, but it's taking, first of all, if I take a vector inside of the set. Now, first of all, what is a vector? Well, a vector is actually defined to be a function here. So it's any function of the form m times x plus b. Okay, so if I scale the linear function, what do I get? Well, if I scale the linear function, I get m alpha x plus alpha b. Now, the argument we need to make is this still linear? Well, as long as m times alpha is a real number, which it is, because a real number times a real number is a real number, and alpha times b is also a real number. Therefore, if you scale a linear function, you get another linear function. So take, for example, 3x plus 5. If I scale that by, say, 2, then I get 6x plus 10, which is still linear. Similarly, if I now take two linear functions, I'll call them x and y, and add them together. Now this gets a little tricky because you got to watch your notation and think about what you're saying. Let x be the linear function. We'll call it m1 x plus b1, and we'll call the vector y the linear function m2x plus b2. If I add these together, then I get m1x plus m2x plus b1 plus b2. And immediately, this does not necessarily look like a linear function unless I factor out an x from the first term. So I get m1 plus m2 times x plus the sum of b1 and b2. Now this looks like a linear function where the slope is m1 plus m2, the sum of the two slopes, and the y-intercept is b1 plus b2, the sum of the linear intercepts. So if I add together two linear functions, I still get a linear function. Here's one where we have a bit of a problem. An exponential function is defined, or we'll define it here, to be any equation of the form a times b to the x power, where a is any real number not equal to 0, and b is any number greater than 0. We don't define exponential functions for negative powers because that creates a problem mathematically, and 0 is not a very interesting one. So will this work? Well, first of all, if I scale an exponential function, so let x be the exponential function a times b to the x. Now, if I scale alpha, x by alpha, I get alpha a times b to the x. And on first sight, you look at this and you say, oh yeah, this is just an exponential function with coefficient alpha times a. However, if alpha equals 0, then alpha x is equal to 0. And that's not an exponential function. You can't have, first of all, a coefficient of 0. And even if you did argue, well, I could just write this as 0 times 0 to the x. First of all here, and this is still equal to 0, by the way, as long as x is not 0. But if I take 0 and I multiply it by any quantity, I get 0. And so 0 times 0 to the x, that violates the definition of an exponential function. A can't be 0 and the base can't be 0. So already, this is not a vector space. Who cares, right? I mean, why would we go through all of this stuff? Well, part of it is kind of thinking about it and doing the algebra and showing that the set is closed under scalar multiplication and addition. Most theorems will use the terms vector space. If V is a vector space, then the following conclusion takes place. So vector spaces do arise, and they do arise in theorems, and so just having kind of a recognition of what that means is useful. So the theory relies on this, and why do we care about the theory? Well, it gives us all the nice mathematical properties to carry out real-world applications and other mathematics that could be either applied math or theoretical math that later on leads to applied math. Also, just as a brief synopsis here, you can have something called a subset, which, in other words, a subset is a set that lives inside of that. So, for example, if we're looking at all ordered pairs where x and y are both real, then ordered pairs of the form k comma 2k, where essentially the y component is double the x component, is also inside of V, but that belongs inside of its own shell. All of these vectors here, or ordered pairs, belong inside of that. So is a subset, what about a subset of a vector? Is it a vector space as well? Do you get another vector space if you take a subset of a vector space? It's not in general true. However, since you're operating on either vectors or other components, all you really need to check is that the closure properties hold. If the closure properties hold on the subset, then we call it a subspace. Again, mainly just for familiarity purposes.